Welcome back, everybody. I spent the morning working on your homework. So homework 1, the glitch that we had where you weren't actually able to submit it because you got an error message, I fixed that, no worries. Those of you who had all 93 right, you have submitted it and you're fine. There's 1 or 2 people that still have a few to go and you can keep working on that. Homework 2 is not yet done. So you have one brief shining moment in time where you have no homeworks hanging over your head. You do, however, have a quiz. That's on Wednesday. So please do that before 1 o'clock on Wednesday so that we can go over it in class. All right. So I want to do a little reviewing before we start the example that we're working on because terminology is going to kill us otherwise. So level 1, level 2. Levels are always context specific. So far we have only dealt with one type of context, and so these levels are unambiguous thus far. So when I say inference, I mean words like between, within, inter, intra, which goes in which column here. Level 2 is which ones? Between, capital letters. Give me a synonym. Inter. Very good. That must mean that level 1 is within and intra. Yes. See? So those are conceptually what each of the levels are referring to. What kind of variability? Now when we get into the more technical side of the model here, what is the name for an error term at level 2? What do we call it? Both of these, by the way, start with R's, so that's not going to help us. This one is random. So I use the term random effect as the umbrella term under which there are 2 kinds of random effects that you know, right? Random intercepts and random slopes. Now I had a few of you on, I think the first quiz, get confused at this point and say, well, if random effects are level 2, then fixed effects are level 1. Correct or incorrect? No, it makes sense. You're like, well, the opposite of random is fixed, so nope, nope. What is the variance term at level 1 called? Residual, yes. What is the E that we use in the equation? Yes, and every time I do this, it usually tries to change it to something else. So, there. No. And what symbol am I using for random effects? Those are U's, yes. So I'm trying to be internally consistent in the notation. If I were looking in documentation in SAS or Stata or otherwise, and I want to know what the place is called that holds my random effects, variances, and covariances, that is the what matrix? G, hooray. And the one that holds the residual variances and covariances? R. You put them together and you get V. Yes, hooray. So, Gesundheit. Kinds of predictors. What kinds of predictors can go in the level 2 model? People, things. Yes, I'm going to take all the synonyms here. People, things. Time invariant, indeed. Time invariant. People, things. Here, we'll move this to a new line. Time invariant predictors. What kind of effects can they have? Fixed, random, or both? Time invariant people, things at level 2. Can they have fixed effects, random effects, or both? Fixed only, random only, or both? Let's put it right that way. Okay, we got 1 vote for both. Anyone else want to vote? 2 votes for both? So far in any of our examples, have we put any people things on our random line? No? So you want to reconsider? It's fixed only. Fixed effects only, but thank you for being willing to be wrong. Wrong answers are highly diagnostic. People things can have fixed effects. There is no higher level in the model at this point over which we could have a random effect. If we had a level 3, then people things could indeed have random effects also. So what kind of variables then can be part of the level 1 model as a predictor? Time what? Time varying. Time varying. I'll put that here, and I'm going to put time things here as the analog, right? Things that are measured at each occasion. Can level 1 variables have fixed effects, random effects, or both? This is a both, and just indeed fixed and or random. We'll say. Now I'm saying and or and thinking about it as significance, but in practical terms, if you have a random effect, you have a fixed effect too. It always starts with fixed. We can add the random if it's significant. So you can have fixed effects at level 1. Those would be fixed effects of time things, and you can have fixed effects at level 2, which would be of time invariant things, people things. So as we say, random is for level 2, residual is for level 1, fixed effects are at both levels. Why this gets tricky is when you specify it in terms of an equation. Let me pull up the lecture that we were looking at last time as an example. When you specify it as an equation in multi-level form, such as that one right here on slide 15 of lecture 2, it looks like the fixed effects are in the level 2 model, and they are. But the variables that they apply to are in the level 1 model. So the fixed effects in this picture are the gammas. They are all level 1 effects because they pertain to these level 1 variables. So in contrast, we look at this slide right here, slide 17. Gamma 1O and gamma 2O. Those are the fixed effects of linear and quadratic time varying age, so they're level 1. We have gamma O1, that's going to be the main effect of time invariant age or cohort. That's level 2 because it's predicting the main effect is predicting beta 0. And then gamma 1,1 and gamma 2,1, those are interactions of age cohort with age, so those are cross-level fixed effects. They don't go with just level 2 or level 1, they go with both. So fixed effects can be at any level or across levels. Random effects can only be somewhere above level 1. If you only have a 2-level model, then random effects can only be at level 2. If you have a 3-level model, random effects can be at 2 or 3. But we'll get there later. Any other terminology things you want to go over in this context? So in terms of R square, the alignment of these columns also tells us which kind of pseudo R square should be relevant for these fixed effects. Time things and time varying things should account for residual variance. Level 1 fixed effects should capture level 1 residual variance. Likewise, level 2 fixed effects as main effects should capture random effect variance. A main effect should capture intercept variance, whereas interactions with time invariant predictors should capture whatever random slope variance we have. It gets tricky when you have multiple piles of variance, but we will keep going over this and over this and over this until it is less tricky. Okay. Other questions? Okay. As an aside, before I forget, so off-topic remark, How many of you have ever had a data task where you did the same thing over and over and over again and it was super repetitive and you thought to yourself, can't there be a way to automate this? Yeah, everyone, right? I once spent 6 weeks doing something by hand that I later learned was a 5-line command in SPSS that was built in, the aggregate command. Seriously. So if you ever find yourself in that situation, stop and be like, what would Lesa do? Does she have code that she's already written to solve this problem? Because odds are good, I have. I've worked with a lot of different data, and in particular with SAS, I've worked with a lot of these sorts of annoying tasks. So I'm going to use you, Katie Jo, as she was known until 3rd grade, but not anymore. So she was trying to come up with a power analysis, and she got data from someone else that looks like this. She sent me. These are individual text files. If you open them up, and if I can open it, it's a weirdly formatted file. Hang on. Let's change an extension so that we can see what it looks like. Yes, I want to change it. They all look like this, where there's information at the top and then a whole bunch of data. Now, Katie, what were you going to do last weekend? And what did you do instead last weekend?
Played with Alexis.
Yes, played with your baby. That is the correct answer. Because I told her not to do that. So I gave her a program based on something else I had written. So again, it took me 5 minutes, 10 minutes to do this. So I'm happy to help you if you're in the situation. You can tell SAS to go into that folder, make it a list of all the file names, and then one by one import each file. It appends the name of the file as a new variable so you know where it came from, and then it dumps them all together, deletes the individual files. It takes the information about which subject it was out of the file name, saves it as a variable, and then converts the rest of the file to numeric. Okay? So this much code to save her weekends. So if any of you are in the situation where you're working with raw data files where there's a whole lot of them and you have to do the same thing over and over, or there's any kind of cleaning type activity where you're going to have to do something manually, stop. Stop and send me an email. Describe the problem and I will hopefully have code that can help you, okay? All right. There's my public service announcement for today. I want you all playing with your babies or your friends, or whomever, right, that is better than doing this. Okay. So back to our regularly scheduled program. This is going to be the topic of your next homework, homework 2, practice with longitudinal models in accelerated time. So I wanted to go over what the code and interpretations look like for these models because they can be tricky. This follows the material in Chapter 10, the first part, fairly closely, although the example data are not exactly the same. It's pretty much the same story, though. So these are real data. They come from a study I mentioned last time, the octogenarian twin study of aging, where they took same-sex twins in Sweden that were 80 to 100 at time 1, measured them every 2 years, for up to 8 years. Quite a bit of attrition throughout the study, as you might imagine. And the questions were things like, what does healthy aging look like? What does unhealthy aging look like? And does it all go together when it goes? These are the types of data that we'll see for twin models, multivariate models, and other kinds of things coming up. So there are multiple variables related to time that I had to create. So I want to go over this because it can be complicated when you have multiple kinds of ages and times. I had a variable in the original data set called comp age, meaning composite age after aggregating various different sources to make sure that it was indeed correct. Comp age is time varying. So this is their age at each occasion. It's time varying. I subtracted from it a variable that was their age at wave 1. That new variable then is time and steady, where 0 means this is your first occasion, and then After that, how much older are you than when you walked in the door? So in doing this, time is purely within persons. It's purely longitudinal information. How much older are you now than you were at baseline? For the purposes of making pictures, I created a rounded version of it because this is slightly unbalanced across people. It was about every 2 years, but of course not perfect. So I rounded time to the nearest 2-year interval so that we could make pictures including it. Then comes the cohort variables. So age in this study is both between and within. That's why I have to worry about these types of models here. Age has variance that's within persons, that's related to time here, and we have variance in how old they were when they started. The latter I'm calling age cohort, and I'm using their age at the first occasion, and I've centered it at a convenient value. 85 was near the mean at the beginning of the study, so I picked 85. I also have another version of time varying age centered at 85. So I'm using the labels here to try and keep track of these things, and a rounded version of it. So just to repeat here, comp age is time varying. Comp age 1 is their age at the beginning. I am creating time out of that, which is a purely level 1 variable. I also have another level 1 variable that is time varying age that is a mixture of between and within person variance. It's their exact age. And I have age cohort, which is purely between. We will end up using these two to start, and then later replacing age time with time. And we'll do the same thing with respect to years to death, but we'll do that one after we do age first. And just to remind you, when you're centering variables in SAS, you cannot do so in open code. All data transformations have to happen within this data set and then run combination. That way it knows which data set you're trying to do the transformations on. So in this line of code right here, I am creating a new data file called octo-all. It's doing this find and replace thing from, that's what set means, the data file in this octo location, which is defined right here, called the same thing. So simultaneously, I am reading data in from a permanent location into the work file so that I can do stuff to it. That's the same code there. Work is implicit if you don't write it, and adding all of these centered variables. All right, with me so far? Okay. Now let's see here. Empty model. What are empty models for again? How much variance is between versus within? So those proportions there, those interclass correlations, are those the proportion between or the proportion within? Those are the between. So those are level 1 or level 2? 2. Those are the cross-sectional part or the longitudinal part? Cross-sectional, yes. So time varying prose recall as a measure of memory is our outcome. 40% of that is due to person mean differences. Some people had better memory than others all the time, on average. Time varying age has an interclass correlation of 0.5. So roughly half of the variance in age is between persons, is cross-sectional, is because we sampled people of different ages to begin with, and half of it is longitudinal because we watched them age over a period of up to 8 years. So because this interclass correlation is somewhere between 0 and 1, we have to worry about differentiating the between and within effects of age. What would it mean, here's a review here, if it were 0? All within. And does any of this apply then? No. And this is why we hadn't talked about it until this point. If time is all within, meaning everyone's at the same point in time when they begin the study, you don't have to worry about differentiating effects of cohort from time. What if ICC were 1? Then it's all between, and this is actually a time invariant predictor. That's what it would be if this were a purely cross-sectional study. But this is half and half. So the fact that this is greater than 0, that's why all of this is relevant. The fact that what we're used to thinking of as time is actually partly between, that's why we have to worry about differentiating these effects. Picture time. This code is a bit dated at this point. It was written back before SAS outputted things in HTML by default. It still works though, and this part of it is the part that's antiquated. The other part is I wanted to show you how to make the kinds of pictures that I put in my presentation, such as this one. So this picture combines the output from a saturated means model that's shown by the heavy black line with the individual trajectories. So I find these pictures can be very helpful in describing your effects of age. So here's how I did it. First off, here's my means model. So note a few things here. This is unbalanced data, so I had to create a rounded version of these variables to get means and make a picture out of. I'm not using those for analysis though. I'm only using those for description. So I have my subject ID, which is called case. I have round age, which is age rounded to the nearest 2 years. That is on the class statement, and it's on the model statement, meaning that the model is going to estimate as many means as I have unique values for round age. What would happen if I forgot that part? What if I didn't round it? Given that this is unbalanced data. Yeah, it would blow up. Why would it blow up? Because in putting this continuous variable age on the class line, it's telling it to estimate a mean for every unique possible value of age. So I'd get, 89.3, 89.35, 89.36, 89.37, and so on. So it will blow up. That's why I have a rounded variable instead. Every 2 years, you could pick whatever rounded interval makes sense for your data, but this is just to get a picture again. I then asked for what the actual means are predicted to be at each occasion, and I saved that table, which is called LS means in SAS, to a new data set called age means. So on the ODS output, let me pull up the internet with all of my various bookmarks here. This one's for Glimix. I will find the one for Mixed so I can show you where this stuff comes from. In case you haven't memorized the SAS documentation yet, just on the off chance. So I'm asking the SAS guide here, SAS Mixed. I have a link to this website on the class webpage. Under details, there is ODS table names, and this is where all this stuff comes from. So everything that shows up or can show up as output has a built-in SAS table name. So we've used some of these before. You've saved, for instance, InfoCrit. That's the information criteria table that has the -2 log likelihood and the number of parameters. We use that one to do -2 log likelihood comparisons. We've also saved CoveParms. That's your variance components. So if you want to save a piece of output, you just have to figure out what SAS thinks it's called. LS means output, which for whatever reason they decided needed a hyphen here, is called LS means. So I am taking that piece of output and saving it to a SAS data set called age means. I am then taking that data set, adding an ID variable, and I am filling in values for age based on what the round age was, and I'm moving the means that were saved as estimates into the pros recall column. That is, what I am doing is pretending that those means came from a real person. I'm moving the information about their estimated means into the DV column, I'm moving their round age information into the age column, and I'm giving them an ID variable with a value of -99. I picked -99 for two reasons. Number one, odds are good that you don't have negative ID values, right? And if you sort by ID, it will be first. So I then sort my original data. I sorted the data of means here, and I merged them together. And that's the data that I used to make this plot. So you can label and customize everything like the axes that you're using. The symbol specification is the thing that I wanted. The first one is going to be for the means that are from the means model. So I told it to give it a black line that's very heavy. And for all of the other ones, I did not tell it what color it was or what marker it was, and so it's just going to cycle through all of the colors repeatedly. And then y equals x, y by x equals ID variable down here, and that's how we get this picture. So here are the means. Here are the standard errors of the means. Now this is a measure of memory. Does anyone notice anything that looks maybe a bit odd about this plot? It's negative, and this is account correct. So you can't have negative, but this is what SAS gave me. Why? Well, let's look at the x-axis here. How many people are contributing to the predicted means by the time we get out to like 96? Like 2? Right? You can tell that based on the picture. You can also tell that based on the size of the standard errors for those means. So this brings up an important distinction in the means that SAS is going to give you under saturated means versus what you would get if you just ran descriptives. These are model estimated means that SAS is coming up with as if the data were complete. It's under an assumption of missing at random. And that's why it's taking the trajectory downwards, because it's trying to figure out what this would have looked like if everybody kept being measured. Obviously, that is an exaggeration, but that's what it's trying to fit. It's trying to come up with an average trajectory that combines data from different people that the model is then trying to reproduce. So would I report this in a manuscript? No. I would probably cut this off about here if I were going to make this picture here, because after this point it's a little suspect. Question, Heather? Because symbol 1 is the first case in the data set, and because I called them -99, they go first. Yep. Yeah, you can use this to specify what exactly you want each person to look like based on these symbol statements. There's also things now, this is gplot, which is an older one. The newer ones are called SG, like SG plot, SG panel, SG scatter, and they have things where they'll automatically cycle through patterns and colors and stuff like that, so you don't have to manually do it if you don't want to. But yeah, that's how I made the symbol 1, because I knew the first case was going to be the means. And so then I was able to draw that. Yep, it's the next case down that you're plotting. And it knows who is who because of this right here. This is y by x equals case. So it understands how to link the data together from the same person, draws a line to connect them. All right, so I have lots of examples of pictures and stuff. Again, if you're ever in the need to do something, ask me for examples and I'd be happy to send them to you. So this is what the model is trying to fit, this black line. So here is an example then. I did some preliminary analyses to figure out what the best unconditional time model would be and came up with random linear. So this is age as time. So the reference point for the intercept is not time 0 here. It is age 85. Note what's not included in my code that normally shows up after random. Starts with another R, controls the R matrix. Repeated, yeah. Why isn't that here? The reason I don't have a repeated is because I'm invoking the default repeated, which is type equals VC. But in this case, I really couldn't have any other kind because I have unbalanced time. There's no common R matrix that all of the cases can share. So there's no way to structure it like Topolits or any of those other kinds of forms. So here's my G matrix. We'll do a little SAS review. We haven't done a whole lot of output lately, so that's good. What's that? What's 10? So you already told me what lives in the G matrix, right? G matrix, level 2, between variances that are random effects. So what's 10? Feel free to read from the table. Random intercept what? Need one more word. Variance, yes. That's not the random intercept for any particular person. It's the variance across people. I don't have the equations here. Would you like to write an equation with me? Why not, right? We'll do a little reviewing. You can do this in Word, by the way, if you go Alt and then equal sign. The equation editor pops up. So I'm going to do pros. I want this over here. There. Pros, if you do underscore, that's how you get subscripts. I'll go TI and then hit spacebar and it jumps down. Equals, what goes first in my level 1 model? What goes first? We need some placeholders. What do I use for placeholders? Yeah, beta. Beta are my placeholders. I need a beta 0. So I'm going to go slash and then type beta and hit the spacebar and it goes chink. And then I go underscore 0 I think. Sound effects optional, but just ching. That's like a happy little. Plus, what else do I need? What comes after 0? Yes! I swear I'm not trying to trick you. 1. What is beta 1 for? Age time. What kind of subscript does age time need? Does it get an I or a TI? Is age time a time thing or a people thing? Say it louder, Amy. Time thing. So that means I need a TI. And I'm going to put in my centering, like that. And do I have any quadratic terms in this model? No. So what else goes at the end? Residual. I do E, you guys can go R if you want, whatever. So long as you're internally consistent in your notation, you can use whatever notation you want, but that's what I do. So this is, I'll label these here. This is level 1. Now I need level 2, I need 2 equations. One for the intercept. And one for the slope. So I'm labeling these here just to try and keep track of what the equation is for, what it's predicting. Nope. Try that again. There. Okay. What goes first in my level 2 equation for intercept? I need a fixed effect, right? Need a fixed intercept. What letter would you like for that? Yeah, I like gamma. Other books use pi, and that makes me crazy because pi is 3.14, and that's it. Like when I see that, I can't unsee that. Just like when I see factorials in math, I always want to pronounce it as an exclamation point, like 4. Like that's. So yeah, I do gamma. Gamma. What's my subscript for my gamma here? Which beta are we predicting? 0. And this is the first predictor of beta 0, so it gets a 0. Actually, first term, I should say. There. And do I need anything else? I need a U. I could also pick squiggle 1, which is common in most books, but I can't draw that on the board, so I've never used squiggle 1. There's squiggle 1 and there's squiggle 2. I'm not sure what their names are, but if you look up the Greek alphabet, that's what it says. Squiggle 1, squiggle 2. Oh, nope, hang on. 0, that's an I. There we go. And I'm going to do the same thing here. This one, I am predicting beta 1, so I need a 1O on that gamma. Likewise, predicting beta 1, I need a 1 on my U. There you go. Ta-da! So now, we can look at this and try to do a little mapping. 10 is the random intercept variance. That's the variance across people in my U0s. That's individual differences in memory at age 85. It's specific to when the centering point is for the predictor because we have a random slope for the predictor. Likewise, 0.12, what is that? That's the slope what? One more word, actually several more words, but slope starts with a V, variance. Now I'm going to pick on you for saying slope because that's right, but of which predictor? Age time, and it's linear. It's the linear effect of age time. It's the variance across people in the linear effect of age time. What is this thing? It's a covariance between your intercept and your slope. So it is the relationship between your level at 85 and your individual difference in change. So the form of this G matrix right here, the form of this G matrix that holds my random effect variances, my differences across people at level 2, is unstructured. Each of these values gets to be whatever it wants. Forever and ever, amen. Type equals UN on the random line. Okay. I didn't print the R matrix, but here's the last piece of the puzzle here. 7 is what? And again, feel free to read from the screen. Residual variance, that's my E variance. That's my why are you off your line? I gave you your own intercept, I gave you your own slope for age. Now relative to the 93 question homework that you just got finished with, this is a relatively simple model, right? There's only one catch. There is no such thing as time 0 here. Well, we're used to talking about like the first occasion being our reference point. Not this time. We have a new reference point. So the intercept is 4.7 for what? For 85, yes. It could be the first occasion, it could be the last occasion, it could be not observed for a particular individual. But that's the expected value at age 85 from this model. Now the slope. It's negative, it's significant. For every year older than 85, what happens? It decreases by half a point or so. So there's my random linear model. Am I done? Write it up, turn it in. No. I have committed the cardinal sin of smooshing. This is my term for it. I have shoved the cross-sectional effects of age and the longitudinal effects of age into the same minus 0.5. I'm assuming age convergence in this model, the idea that it doesn't matter when you are 85, it only matters that you're 85. An 85-year-old in the year 2000 is the same predicted value as an 85-year-old in the year 1950. So I have pictures. Sometimes I make pictures in SAS, but more often than not, I make them in Excel. And that's because usually the people that I'm working with may or may not have SAS or whatever particular program I'm working in, and everyone can work in Excel. So I like to make pictures in Excel for ease of sharing them with people and because pedagogically they help describe what's going on. So I have a picture here, age convergence. The slope of the red line is what our model currently predicts. And to make that, I created a series of age values ranging from -5 to 11. That's relative to 85. I inputted the fixed intercept and the fixed linear slope, and I created a predicted outcome. I included placeholders for all this other stuff here, but in this model it doesn't matter. It's just intercept plus age times slope. So this is potentially problematic because it assumes the between person and within person effects of age are the same. And we know that half of the variance is due to each source. It also assumes that there's no cohort effects, that all you need to know is how old someone is and you can calculate their predicted value. So let's fix it. I'm going to go borrow my equation. And we're going to add to it. More generally, whenever you have a level 1 predictor that has level 1 variance in it within persons and level 2 variance in it between persons, it has to show up at both levels of the model. The way that I'm doing that in this context is to introduce a variable called age cohort, which is their age at the beginning of the study. So I am adding that. This is going to be gamma what? Yeah, it's like, is it 01 or 10? Yeah, it's 01 because we're still predicting beta 0, and now this is the first predictor of beta 0. I'm going age cohort is what I'm calling this. Does age cohort get an I or a TI? Got one vote for I. Anyone else want to vote? I, another vote for I? Yeah, I. Age cohort is time invariant. It is a people thing. Each person has one value. It is their age when they started the study. And I centered it at 85 also. In your homework, I gave you deliberately two different values to center age and cohort with. In this case, I'm keeping them the same. It's an interpretation choice. There isn't really a right or wrong answer for that. And I'm going to add the same type of term to my level 2 slope. And now this one gets to be what? Gamma. This one is a 1, 1. Because we're predicting beta 1 now, so that's why the first term is a 1. And this is the first predictor of beta 1. And this is the point at which people's heads usually start to hurt, mine included. Because there's two kinds of age in the model, but they're doing different things. So gamma 1O is the effective age time at level 1. Gamma O1 is the effective age cohort at level 2. And gamma 11 is their interaction. Yep. Gamma 1O is the effective age time at level 1. Gamma O1 is the effective age cohort at level 2, and gamma 11 is the interaction of age at level 1 and age cohort at level 2. And now you know why I pound caffeine while I have to teach this stuff, because it's kind of hard to say it the right way each time. Age cohort allows for the potential of a differential cross-sectional effect from a longitudinal effect. It controls for when you are 85. At the beginning, at the end, were you ever 85 during this study? Age cohort is a level 2 between person time invariant predictor. In theory, which variances should age cohort right here capture? This is the main effective age cohort on the intercept at level 2. What kind of variance should it explain? The one in its line, U0, intercept variance. Likewise, this effective age cohort on the slope should explain this slope variance. That's what should happen. What actually happened is not that. Instead, the slope variance went up, the intercept variance went down a little bit, and the residual variance went down a little bit. That's not supposed to happen, but it did. That's pseudo R-square for you in real data that's unbalanced. It goes all over the place. This is an example in which it might be easier to calculate total R-square rather than looking at the change in each piece. Okay. But now we get to practice interactions again. So we said before that the intercept was for an 85-year-old, right? Now we condition it further on age cohort. The intercept is the predicted value at age 85 for somebody who started the study at 85, meaning at their time 0. So this reference trajectory right here, built from intercept and age time, that's describing what the effect of aging looks like for somebody who starts at 85. If I'm 85 when I walk in the door, I'm predicted to have PROS recall of 5.5, and for every year older than 85 I get during the study, I decline by about 2/3 of a point. That's me, my cohort. So note that this is a bigger decline than what the previous model predicted. That's for 2 reasons. Number 1, this is conditional on somebody who started the study at 85. Number 2, it's reflecting only longitudinal information. The previous model had a less negative slope of age time, in part because it hadn't adjusted for age cohort, which actually has a positive effect, which is significant. So how do we talk about that? I would think of this as a contextual effect. It's a cohort effect. It's over and above the effects of age that are already in the model. So we have the intercept of 5.5 for people who start the study at 85 when they start. For every year older you are when you start the study, at 85, you're predicted to be higher. So you looked better at 85 if you came in when you were 88. Even though we don't know what you looked like at 85 because you came in at 88. The effect of age cohort on the slope is non-significant, but it's negative, meaning that people who came in older have a slightly more negative slope, 0.02 more negative per year. And this is the point where we need a picture. So you have the Excel sheet that I used to make this. This merits some explanation. First off, the dashed red line, that was from the previous model not controlling for cohort. That's the model that said for every year older you are, you go down a half a point, the end. That is based on the aggregate trajectory lumping different groups of people together. Because some people were sampled from 80 to 88, some people were sampled from 84 to 92, some people were sampled from 90 to 98, and so on. The separate lines that are in this picture, the blue, the pink, the green, these are predictions from the model after controlling for cohort differences, after controlling for when it is you entered the study, and thus what your predicted value at a given age should be. I've deliberately drawn these lines so as not to create predicted values for times that were not observed. That's why this blue one here, this is for people who started the study at 80, and so they have a predicted value at 80. But the people who started the study at 84, I did not create a predicted value for, and likewise for the green. So if we look at the slopes, the green slope for somebody who started the study at 88 is slightly more negative than is the pink slope or the blue slope. That's the cross-level interaction between the two. Older people decline a little bit faster, non-significantly so in this case. Their slope is more negative by 0.02 per year. With me? If you're not, feel free to admit it. This stuff is tricky. Now the intercept effect. I've drawn in the intercept here with the dashed line to help us remember what the intercept is in this model, which is 85. So that positive effective age right here of 0.4, that is describing the fact that if you extrapolate backwards, the later you started, the better you would have done at 85. So the people who were still around to start the study at 88 as a group looked better at 85 than the people who started the study at 80. And we talked about this last time, right? Who's still around to start a study at 88? The super seniors, right? Who's not around? Less super seniors. So these are different groups of people with non-random missingness, non-random selection. So it looks like you really can't draw one line through this group of people and have it lump everybody onto one trajectory. It doesn't exist. If this were the right model, these lines should be right on top of each other. There should be no cohort effects. So the extent to which these lines diverge from this common trajectory one can use as evidence of cohort effects, or that really it's not just age, there's something else. Because if it were just age, controlling for your age at the beginning shouldn't matter. To show you what it would look like when you get a better fit, I have years to death. So I created the same types of variables where we have time varying years to death and your years to death at the beginning as the cohort indicator. And I made this picture, rounded to the nearest 2 years. And this picture shows evidence of what in the aging literature is known as terminal decline. The closer you get to death, there's the cliff. And there's a lot of research suggesting, trying to find where the cliff happens for different kinds of people. So the best fitting unconditional model using that as a time metric was actually quadratic. And I know it sounds very morbid, but I've named these variables dead time, as opposed to age time or something else. So if we look at the pattern here, 6 years to death, you're predicted to have a prose recall of 6. Your instantaneous linear slope at 6 years to death is minus 2/3 of a point per year. And as you get closer and closer to the bad day, what happens to your slope? Which pattern is this? More negative, yeah, accelerating decline, that's the pattern here. But this is lumping different people together. So if we look at the picture here, some people started the study with a long ways to go, some people started the study with not so long of a ways to go. To what extent do cohorts matter? To address that, I put cohort, dead cohort, as a predictor of the intercept, the linear slope, and the quadratic slope, and got a big pile of nothing. So if I were interested in trimming the model down to just what was needed, I would go sequentially, take out the highest order interaction term, see if the second order interaction term needs to be there, and so forth. But these cohort effects are fairly minimal, still a slightly positive effect on the intercept, more negative linear slope, less negative quadratic slope, and here's what it looks like when you plot it out. And this is probably the best example in real data that I've seen. This is evidence for lack of cohort effects. The trajectories align pretty close. So show of hands, who thinks this is confusing? Yeah. Me too. So don't do it this way. Do it this way instead. Just have time. Just have time, and then throw in the predictors to see what moderates it. So here's the same picture, plotted as a function of years in study. So this time metric is agnostic as to theoretically what's causing change. Is it age? Is it dying? Is it whatever? It's agnostic, it's atheoretical, and that's actually good, because it then allows us to compare and contrast different explanations as to what is causing change. Time in study is purely longitudinal. We don't know at this point why some people walked in the door better than others. It could be that they're healthier, it could be that they're younger. Bleh. We don't know why some people fell off the cliff more quickly or to a greater extent than others. Further, because we're not extrapolating past any occasions that don't have enough cases, all of the means stay positive because we do have people who made it all the way to the end of the study at year 8. So it ended up that we need random linear for time. So in this case, this works back to the same type of model that we had last semester. At year 0, at the beginning of the study, the average recall value is 5.6. People decline by about 2/3 of a point per year. I can then contrast the effects of age and years to death in the same model. I can use them as competing explanations, where years to death is a proxy for lack of health or the disease process, however you want to think about it. And even though the model has more things in it, I would argue that it's a lot easier to explain. So I have interactions with time for both age cohort and death cohort. So I have both their main effects and their interactions with time. So my reference person is somebody who walked in the door at 85 and they have 6 years left to live. That person, when they walk in the door, gets a 5.4 and they decline by 0.88 per year. So here's aging, these two. If you walk in the door older, you have worse memory when you walk in the door. Here's your cross-sectional effective age. The effective age on the linear slope is non-significant. You do not decline faster if you are older. However, if we look at the death cohort effects, they're much larger. And because these are both scaled in per year, I can directly compare them. So for every year closer to death you walk in the door, you're doing worse by 0.5 point. And for every year closer to death you become, you decline more quickly by 0.06, and that is significant. So I like this version because it's easier for me to think about, here's my longitudinal effect, here's my cross-sectional effect, the end. And here's a picture then that shows predictions for different kinds of people, what should happen to them during the study. In Chapter 10, I also show these same types of plots using the other dimensions as an x-axis, so you can plot a years in study model against age or against death cohort. Any variable that's in your model you can use as your x-axis. So, take-home message, big picture. If time has between-person variance in it, you have to worry about this. You have two options for how to worry about it. Number one, use your original accelerated variable, such as age or years to death, the variable that contains both within and between information at level 1, and then talk about cohort effects at level 2. Or just have time at level 1 and then use the cohort variables purely at level 2, so they're not intermingled. I like the second one much better. And words. Words, 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 words. I will remind you, as it's in Chapter 10 and it was in the presentation that I gave, algebraically, you can get from one of these models to the other. Even given the most complicated set of fixed effects you can think of, you can rearrange the model so that they're equivalent. So if anyone tries to tell you that just using time is wrong, say, algebra. No, it's not. How's that? So I hope to have your assignment 2 done by Wednesday so that you can start working on it. But it will be a story like this, except it won't be about death. It will be about adolescence, because that's a lot happier. No one's going to die in your simulated data homework. And you won't even feel like you want to die because it's not going to be 93 questions this time. So that. So any questions? All right, so next time then we'll go over the quiz at the beginning of class. New material has been posted. We'll do more with time varying predictors. This was your preview of that. So come back next time. Office hours start now.